All right, Saintsman, I've got lesson 8.3 for you here, proving triangle similarity through side, 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 and side, angle, side. We just did the angle theorem to show similarity between two triangles. It's the only theorem that we had so far. Now we're going to work with this one, SSS, first of all. Now, what SSS meant that we had to have with congruence was the following, right? It was that we had to have three sets of sides that all were the same in two triangles, and correspondingly that would make these triangles congruent. There's a postulate, but here we're going to be talking strictly with similarity. And I remember what similarity means. It means proportionality. So in this case, let's see here. If we have So if the corresponding side lengths of two triangles are proportional, right, then the triangles are going to be similar. And it has to be all three sides. Now, it worked differently with angles, right? Because angles were looking for congruence. And if two were congruent, then the third one had to be congruent. This is going to work like this. Let me go ahead and just draw some diagrams here. So drawing two triangles. This guy is going to be... Second triangle is going to be larger. And what we're going to know about the two of these is that these triangles, ABC and RST, are going to be similar. So correspondingly, each of their sides will be proportional, right? It means that AB, the first and second, right, letters are going to correspond to R and S, the first and second. B and C, second and third letters, right, will correspond to S and T, second and third, and first and third, AC, and first and third, RT. So those will all have a proportion that will be the same for every single one. So let's employ this, because we'll just have one little quick example. We'll do one here for side angle, for side to side, and we'll do the same thing for side angle side. It's a pretty quick and straightforward lesson. So I'm drawing our diagrams just so you guys know. Didn't go anywhere here. So in this triangle HJK on the left, I have sides HJ is 15, HK is 30, and then JK is 5 times the quantity x minus 6. And then I have XYZ, where XY is 3, YZ is 5, and XZ is x minus 5. Now, what our directions are going to be is going to be find the value of x that makes these two triangles similar. But let's make sure that we get the similarity statement, because that's the real key here. Not what it looks like should correspond, but what the similarity statement actually tells us does correspond. XYZ is similar to triangle HJK. All right. So lots of ways to go about this, right? We could take JK, right, which is going to give us a value of x. I'm going to work in blue here. Oh, it won't allow me to. Okay, I think I'm out of RAM memory to do that right now, but that's okay. JK, which will correspond, JK again, second and third, has to correspond to YZ, right? So jk to yz. Let's take another two values, jk to, let's take hj right here. hj, which is the first and second letters, means that it would have to be the first and second letters xy. And then the other diagram, xy is going to be 3. So that should get us on our way. We're going to substitute those values. jk is 5 times the quantity x minus 6. yz is 5. And then hj is 15 over xy, which is 3. Let me fix these for you guys here. Sorry. My pen is acting up. There we go. So we're going to do a cross product, right? When we do that, and some of you guys are like, well, can I, start to cancel out some stuff? I guess you could, but, why not take a cross product showing that we can do it too, right? Algebraically 5 times 15. And again, I don't want you guys to shy away from those calculations because your calculator can do them. I want you guys to incorporate that thing, okay? Divide both sides by 15 in this case, right? Which of course we could have done all along, right? We could have gotten that and that would have been 5. Right on, we just had would have had x minus 6, right? 15 divided by 3 would have been 5. Add 6 to both sides and x is going to be equal to 11. And that's all I was asking us to do was solve for x. So we are home free. Next is side angle side similarity. All right. Side angle side similarity works like this. All right. So drawing these two, I have x, y, z, and then I have n, p. And the only thing I'm given here is that angles x and m are going to be congruent. Now, here's what this means. Here's what our theorem says. And don't overcomplicate this thing. What it says is that if we have angle x is congruent to angle m, and then we now would need a lot of proportionality to be set up. So it's going to work, right, with these corresponding sides. Side, right? But the angle is included, so it's got to be xy to mn. So when we have that included angle congruent, but then we have these sides proportional outside of that included angle. So xy to mn, the other from angle x, right, it'd be xz would be that other side, and then that would correspond to mp. Then we're going to have similar triangles. Triangle xyz would be similar to triangle MNP. All right. So similarly, right, we had a side angle side congruence between two triangles. Now we have side angle side similarity. Similarity theorem works, right? Of course, because similarly, the way that the proportionality of the side does. But we don't need to prove that third side, right? Which in this case would be x, y, and mp. I hope this reminds you a little bit of like that hinge theorem that we worked with before. That included angle, right, was going to effectively control that open side, right, xz to pn, and that proportionality is going to exist between those two. So let's do a little example and we'll be done here. Okay, we have a right triangle. And then we have an altitude within a right triangle. Something to know about this, by the way, is that when we have the altitude of a right triangle, it creates actually three similar triangles. I'll show you. It actually does it through angle. Make a little note here. This is a little fun fact. Oh my goodness. Oh my gosh. Here we go. Just want to illustrate this for you guys real quick. Take a look. I got my bigger triangle here. So I have, right? And then I have three triangles ultimately. This little guy on the right and then this bigger guy on the left, as well as the outer one. It does it through angle because I have, let's say, this medium triangle right here, right? I have a right angle, right, and a right angle. So that's the medium triangle and the larger triangle. And then, of course, I'm going to have the angle right here, which is reflexive to both. Therefore, those triangles have to be similar, okay? These triangles have a couple parts to discuss. There's a hypotenuse, right, which is the angle or the side opposite whatever right angles we have. But then within those, there's going to be two legs. A short leg, right? In this case of the small triangle, it'd be 9. And then there's a long leg. In this case of the small triangle, it'd be that 12. So let's solve for x here, okay? So x, right, which would be the long leg, right, to 25, which is going to be the entire hypotenuse, will be 12, the long leg, to the hypotenuse 15. All right. Now people wonder, wait, hold on. How do I know that that guy's the long leg here, right? Well, it has to be because in this triangle right here, it's going to be a hypotenuse, right? X would be a hypotenuse where you have 12 as your short leg and 16 as your long leg. Okay. So, winds up being opposite this other side right here. Okay, then we have this thing constructed. Then we're just going to be off to the races. We're just going to take a cross product. We're going to have 15x is equal to 12 times 25, which is 300, right? 4 quarters, 100 times 3, 300. And then we just divide both sides by 15. In this case, that's just going to be 20. All right. We can double check it. A couple ways to go about it, right? If you weren't sure if you actually chose the correct side to be the long leg. Again, you have a hypotenuse, right? We had 15 to 12, right? Hypotenuse of the small triangle, this little triangle right here, to the long leg. Uh-oh. Little crash right there. That always happens from time to time. Okay. As I was saying, this guy right here, that small triangle. So 15 to 12. If I were to go the hypotenuse, which would be x, to the long leg in this other one, which would be 16, right? And then we're going to effectively get the same thing when you do your cross products, right? So 12 times x is 12x, 16 times 15 is 240. Is that right? Yeah, 15 times 8. Okay, yeah. There you go. That's it. I mean, divide both sides. It's gonna be x is gonna be 20. It's that straightforward. So, gentlemen, if you have any questions, of course you guys can reach out to me. Good luck with the assignment 8.3. It's posted in Canvas.